Welcome to BioVivacious. BioVivacious, as you know, is a YouTube channel dedicated to clear fundamental concepts of biosciences. Today we are going to talk about peptide bonds. So peptide bonds is a bond formed between two amino acids. So let us understand how exactly this peptide bond is formed. So we will write the structure of one of the amino acids. So therefore, one amino acid, this is the C alpha carbon atom. So this will have an R group and it will have an amino group and a carboxyl end. So this is the structure of an amino acid. And it is formed between two amino acids. So let us also write the structure of another amino acid. So therefore, C alpha, similar, this is NH2. So two amino acid structures are drawn. Now what happens is a molecule of water is released from this carboxyl end and from this amino group. So therefore, by releasing a molecule of water, if you remove a molecule of water, so what you are going to get is, by removing a molecule of water, you are getting a bond like this. So this is called the peptide bond. This bond is formed, this bond is called the peptide bond. Now remember, peptide bond in a protein, in the formation of peptide bond is not favored. In the hydrolysis of the peptide bond is in fact favored. So which means if a peptide bond has to be formed, investment of energy is required. How much of energy is required? You need to add a 10 kilojoule per mole. Energy is required in order to form a peptide bond. So you have seen that it is by removal of a molecule of water, a peptide bond is formed. So therefore, it is basically a condensation reaction or it is a dehydration reaction. This peptide bond is also known as an amide bond because it is formed between a CONH group. Now this peptide bond is it's pretty stable. In a biological system at a normal temperature and pH, this bond is stable and it can last for about 1,000 years unless there is an enzyme, a biological catalyst which is cleaving this. That is the beauty of a peptide bond. Now, if you look at this, so we are able to keep on assembling peptide bonds. So therefore, with one amino acid number 1 can be linked with the amino acid number 2 to amino acid number 3, amino acid number 4. So this way we can keep on forming peptide bonds. So we will get a polypeptide, and that is how we make a protein. From your basic knowledge, you know that we can write the structure of this amino acid. For example, we can say that this is a glycine and this is glutamic acid, this is tryptophan, this is alanine. So we can write in this manner. What is interesting for us to see is it begins with an amino terminus and it ends with a carboxyl end. So therefore, we can say that it begins from an amino terminus and it ends in a carboxyl end. So therefore, this becomes part of a polypeptide chain. This we cannot write in the reverse direction like, N, alanine, tryptophan, glutamic acid, glycine, C. This becomes a totally different protein structure. So therefore, when we write the structure of a peptide bond, it has to be written starting from the first amino acid to the carboxyl end amino acid. This is one convention that we need to keep in mind. When we talk about peptide bond, we need to talk about another concept, that is dihedral angle. Dihedral angle is also known as torsional angle. What is this torsional angle? It is an angle that is formed by 4 carbon atoms. So which are the 4 carbon atoms? 1, 2, 3 and 4. So therefore this C alpha is the carbonyl carbon, the amino nitrogen and is the next C alpha of the another amino acid. This is the bond, the angle formed by these 4 atoms are known as the torsional angle. See, what is important for us to remember is this torsional angle can be, you can imagine, let us say that, you know, this is the first atom, second, assume this is the third. If we arrange them in this manner, what we can do is we can generate an angle like this. Okay, so that becomes one plane. And the second angle we can generate it in this manner. This is 1, 2. Okay, so that is becomes another plane. So that is equal to, this is one plane, a second plane. So you have a structure like this. Okay, in the angle created, this is known as the torsional angle. We will be discussing, this becomes so much part of the formation of several the structures of proteins like the alpha helical structure. So, and you can see that this angle you can keep on, you can adjust these angles depending on the charge, depending on the R group of the amino acid. This angle can be adjusted. Now remember, in most cases the maximum it can take is about 180 degree. In the case of a peptide bond, you will see that it is about 180 degree. Then only a trans peptide bond can be formed. So therefore it forms a 180 degree angle, that is in peptide bond. And this angle you can rotate in both the direction. You can rotate it in the clockwise direction. What do we mean by clockwise direction? If this is clockwise direction, you know it is moving in this, that is clockwise direction. So if we take a rod like this, catch with your hand, right hand. So therefore this finger is showing this direction. Okay, the fingers are showing the direction of rotation and it will move in the upward direction. So that is known as the positive rotation. So I will ask you to look at the positive rotation from a different angle. So that is parallel to your eyes. Suppose you have to rotate in this manner, you know that it is rotating in this direction and it is going away from you. We will be looking at it again. So this is a positive rotation. So having understood how exactly a peptide bond is formed, let us look at the characteristics of peptide bond. So first of all, a peptide bond, as you can see, it is a covalent bond. So that is one of the nature of a peptide bond. So you can also see that this peptide bond is planar. What is the meaning of the word planar? Planar means it is plane. So 6 atoms. So that is the 6 atoms are, one is this, 1, 2, 3, 4, 5 and 6. So starting from this C alpha to the next C alpha, these 6 atoms remain, it stays in a plane. For example, it stays in a plane like this. Okay, so it stays in a plane. So that is the important aspect of a peptide bond. Another important aspect of a peptide bond is that this peptide bond, it has a resonance structure. So it has 2 resonance structures. Let us write the resonance structures of this peptide bond. So we will focus only in this region in order to understand. So therefore you have So the peptide bond, you have the C alpha, to that you have this double bond NH and the C alpha. So this is the peptide bond. So what will happen to this is, there will be, at the moment you know that there are two lone pairs of electrons on the oxygen and two lone pairs of electrons on the nitrogen. In the resonance, this is one of the forms it will take. In the second form it will take is, that is the second resonance form, we can write it like this. So it will take, the next resonance form is like this. Okay, it will take a second form. So therefore it will resonate between the first form and the second form. That brings to the second important aspect of a peptide bond. That is, the peptide bond is having a partial double bond character. So in the second resonance form it takes is, now what will happen here? So here there are two lone pairs of electrons, so which is added here, and it will develop a positive charge. So therefore it will develop a kind of a partial double bond character. Now when we look at the partial double bond character, we also need to look at what is the length of the CN bond. What is observed is, this CN bond, normally it is about 1.49 Armstrong. That is the length of the CN bond, a single bond. If it is a C double bond N, that bond length is about 1.27 Armstrong. So what is observed in the case of a peptide bond, this length is about 1.32 Armstrong. So somewhere in between. So therefore this is to show that the peptide bond can have a partial double bond character. Peptide bond can have a partial double bond character. Now what is the implication of this partial double bond character? That is a very simple example. So here is a duster. So for example, on this duster we decide to put a nail. So therefore we are putting a nail on the duster, and you know that you are able to rotate the duster because there is only one nail put. Okay, so therefore there is a free rotation is possible. What if we put two nails here? One nail here and the second nail. So therefore there are two nails. You know that when there are two nails put on this duster, if the rotation, if the movement is stopped. So the movement, there cannot be a movement. So therefore there will be limited mobility because of this partial double bond characteristic of the peptide bond. So therefore if the bond length is small, it is reduced and it has got a partial double bond character. And many books will say that it is about 40% is the nature of the partial double bond character, 40%. Please understand that because of this partial double bond characteristics and unequal distribution of these ions, so this is likely to develop a slight negative charge. The carbonyl carbon will develop a slight negative charge and this will develop a slight positive charge. So therefore this is going to be CO negative and this is going to be slightly positively charged. So therefore when you write C, this is the amino nitrogen, the N2C, this is you can say that there is polarity existing in the peptide bond. There is a polarity existing. Now another important aspect of this peptide bond is the configuration. So if you write in reality how it will look, this C alpha will look like this. C alpha is here, this C alpha will be here. So therefore now you are able to get, let me remove all these that is not needed. So rub that. So therefore, this is going to be in the way in which a peptide bond will exist. So now it is very clear in the plane it forms. Now, what is important here is this C alpha will always exist on either side of the peptide bond. So it will always exist on either side of the peptide bond. We know that if the bulky groups are existing on either side of a double bond, we call that trans double bond. It's a trans. So therefore, a peptide bond has a trans nature. So therefore, it will keep the bulky groups on either side. It has a huge advantage. The advantage is if the bulky groups are on either side of the double bond, they cannot come together. So therefore, it is to avoid steric hindrance. So the proteins are able to fold properly in a protein by using the peptide bonds. That is one of the biggest advantages of having a trans double bond. Suppose if it were a cis double bond. So what we are going to do in order to make a cis double bond, we will just make this structure like this. So this is C double bond O. So this is C alpha. You can see that now here will be the R group. This also let me remove. And this will be the R group. You can see that the R groups are coming closer. As the R groups comes closer, there will be steric hindrance. So a trans double bond will promote formation of a polypeptide chain, formation of a protein. That is what we need to understand from the characteristics of a peptide bond. So we have seen the characteristics of peptide bonds, like it is a covalent bond, it has a planar, it has got partial double bond characteristics, and it is a trans double bond. So, and it is formed between 4 carbon atoms. So we spoke about tetrahedral formation. So these are the points that we need to remember about the structure of a peptide bond. It is very important to label the linkages in a peptide bond. So therefore, let us learn that. So therefore, we have a peptide bond this way. This will be the C alpha and this is the C alpha carbon atom. So normally, the peptide bond is denoted by the Greek letter omega. And in the bond between the amide nitrogen and the C alpha of the next amino acid is denoted by the Greek letter phi. And so therefore there is a rotation around the phi bond. And in the bond angle between the carbonyl carbon and the C alpha of another amino acid is denoted by the Greek letter psi. So therefore these phi, psi are important bond for us to learn other aspects of peptide bond, the protein structure in future. So therefore, remember this plane is on a planar, immobile, double bond nature, whereas around in the alpha carbon atom, mobility is possible. Let us draw this structure. So this is the plane that we have been talking about. So therefore, mobility is possible around this alpha carbon atom only. So therefore, this you can rotate, this also can be rotated. If the phi and the psi bonds can be rotated. Now, what is the advantage of rotating the phi and the psi bond? For example, assume that this is the alpha carbon atom and this is one plane created by one peptide bond, another plane created by another peptide bond. So therefore, you can see that depending on the size of the R group, you are able to fold them. Okay, you are able to fold them. This becomes significant in the formation of alpha helical structure. one important aspect of this, that is the presence of, let me rub this, the presence of proline. Presence of proline. Now, you know that proline is an amino acid. If proline is forming a peptide bond, what happens is, in the case of proline, this is the C alpha, and to the C alpha, if the carbonyl carbon is connected, is linked. Now, the amide nitrogen, it is only an NH. The amide nitrogen has a ring structure, H2, H2 and H2. So you see the shape of the peptide bond here. So it is more towards a cis configuration, this peptide bond. So therefore, presence of a proline is creating a bend in the structure. So therefore, you can see that there is no phi bond, because this is supposed to be the phi bond. There is no phi bond existing here. So this is the typical aspect of proline being in the peptide bond formation in any protein. We will be looking at the issues related to this as we proceed with the discussion.